NASA just launched a probe toward an object 100 times larger than an interstellar giant hurtling through our solar system. What began as a scientific intercept turned into a jaw-dropping discovery. This wasn't just a rock. It moved, reacted, and left behind something impossible. What the probe found changed everything. The moment they decided to act, NASA's bold move. If you find stories like this fascinating, make sure to subscribe so you never miss the latest discoveries and missions. It started the way these things always do, quietly. A single point of light, moving just a little too fast, carved its path across 3 consecutive sky frames. What looked like a flicker became a flag. Astronomers flagged the anomaly from survey data pouring in from Pan-STARRS and the Vera Rubin Observatory, then passed it to NASA's Minor Planet Center. Within 36 hours, X-100 had a preliminary designation and a problem. The object was coming in fast, much faster than any asteroid in the catalog. Its trajectory was hyperbolic, on an open-ended path through the solar system like Oumuamua and Atlas before it. But this one wasn't a pebble. It was a mountain. Estimates based on reflected light and Doppler drift suggested something at least 100 times larger than Atlas, with a radius possibly exceeding 2 kilometers. That put it well beyond the observational comfort zone. "We've never had an object this big coming in this fast from outside the system," said Dr. Anaya Voss, head of NASA's Planetary Defense Coordination Office. It wasn't just an opportunity, it was a test. The decision node came within a week. Orbital Solutions gave NASA a shrinking window, only 58 days to mount any form of intercept. Observation alone wouldn't be enough. If it passed by and left, the secrets it carried would vanish with it. So the call was made. For the first time in history, humanity would try to intercept a massive interstellar object before it left our reach. The mission wouldn't just observe. It would aim to get close, within 1,000 kilometers, and send back high-resolution data that telescopes couldn't dream of. A probe would be launched fast and lean, built to chase something that wasn't waiting around. Sometimes, one mission planner said, you don't get to ask the universe for a second chance. But the size of X-100 wasn't the only reason to act. It was how it moved, and what it might be made of that made it a potential threat. And that leads us to the deeper concern. What exactly was X-100? The closer scientists looked, the stranger X-100 became. At first, the assumption was simple. It was just a giant comet from another star system. But everything about X-100 pushed back against expectations. Its mass was immense, with a density suggesting something more solid than typical icy bodies. Not a loose rubble pile, more like metal or stone. And yet it glowed. Spectroscopic surveys revealed signs of outgassing, jets of gas, probably carbon monoxide and cyanides, bursting from vents as it neared the sun. It was active, but not like a normal comet. The coma didn't behave predictably. The tail curved in reverse. Some emissions appeared in unusual spectra, hinting at compounds not seen in any known comet. More worrying were the fragmentation models. If the object cracked under thermal stress, it wouldn't crumble. It would shatter into high-velocity fragments, each potentially catastrophic in a collision with satellites or future missions. This wasn't just about learning, warned mission analyst Xiao Jin. This was about preparing. If one of these gets captured by gravity in a future pass, we better understand what we're dealing with. And then there was its trajectory, a perfect inbound vector against the plane of the ecliptic. Retrograde odd, not just rare but statistically unnatural. Some theorized that X-100 was ejected from a failed star system, maybe even an ancient planetesimal tossed loose by a supernova. Others noted its acceleration profile, small but measurable, the same mysterious drift that made Oumuamua so famous. Was it natural? Possibly. Was it simple? Absolutely not. We're not saying it's artificial, one analyst said, but we can't say it's not either. And so the next move became even more urgent. If X-100 held secrets, it was time to go get them, which meant choosing how to intercept something that didn't want to stop. Reaching X-100 wouldn't be like chasing a moon or circling an asteroid. It was flying by at over 80 kilometers on a one-way escape trajectory. There would be no second pass, no orbital insertion, just one chance to intercept. NASA had only a few viable platforms ready to adapt. After heated internal debate, they greenlit a modified version of the Draco-class interceptor. Originally designed for planetary defense tests, It would launch on a Falcon Heavy stripped down for speed, carrying a compact spectrometer, high-resolution imagers, and a radiation-shielded data core. No sample return, just a flyby and a flood of data. The mission would need to leave Earth orbit within 29 days. That meant skipping traditional planning cycles. Engineers raced to reprogram the autonomous guidance systems, factoring in the object's high-speed trajectory and gravitational mechanics. To reach X-100, the probe would swing past the Moon for a gravity assist, then accelerate on a hyperbolic burn. Delta V was everything. The probe needed a precise velocity boost to match trajectories, not slow enough to fall behind, not fast enough to overshoot. That delicate thread of orbital timing was a knife's edge. Any deviation of just 0.1% in vector velocity could miss the intercept window by tens of thousands of kilometers. "We're threading a cosmic needle at 80,000 mass," said lead navigator Emma Kulich. "It's not a mission. It's a slingshot with one bullet." Communications would be limited to short bursts relayed through the deep space network with multi-minute lags. That meant the probe had to think for itself. It would switch to auto-intercept mode 48 hours before closest approach. No corrections allowed after that. Heat shielding had to be reinforced, not for re-entry but for solar flux. The trajectory would skim near perihelion, 0.42 astronomical units from the Sun, testing the limits of the probe's internal cooling systems. And if the mission failed, there was no backup. "The stars don't wait," Mission Director K.G. Thorne said. "Neither does X-100. The launch window opened on a narrow December morning. Weather was clear. Ground systems were green. At 0644 UTC, the Falcon Heavy ignited and carved a white arc into the stratosphere. In under 9 minutes, the payload was coasting in low Earth orbit. 3 burns later, it was gone, out of Earth's sphere of influence, already reaching speeds that would break orbit from Jupiter. Mid-course corrections began within hours. The probe's onboard star tracker and optical sensors began scanning for X-100's faint shimmer against the background stars. Telemetry from Earth guided its position for the first few days, but once it crossed the halfway mark, light lag became a wall. Instructions from Earth would take too long to arrive. It was time for the probe to decide on its own. Every 90 seconds it recalculated its trajectory. Every movement had to account for solar pressure, minute gravitational tugs, and the growing distortion of spacetime as it approached its solar perihelion. One course correction nearly derailed everything. On day 12, a solar flare triggered a temporary sensor blackout. The probe lost lock on X-100 for almost 17 minutes. When it reacquired the target, its predicted course had drifted by 46 kilometers. Engineers scrambled to update onboard logic in time, but the craft held. As it neared final approach, it entered intercept mode. Radiation shielding deployed. Instruments rotated into forward lock. The high-speed camera array began firing test images. Blurred stars at first, then a growing gray mass. That was X-100. The probe adjusted one last time, correcting for an angle deviation caused by dust scattering ahead of the object. Everything was down to millisecond timing now. If it missed, it would miss forever. "Imagine throwing a needle across the Grand Canyon," Kulich said, "and having it thread another in mid-air." In the final 72 hours, there was only one task: watch, scan, and wait. Because in the next few hours, humanity would meet an interstellar visitor face to face. It was nothing like what they'd pictured. X-100 didn't look like a comet, asteroid, or anything we've catalogued before. As the probe drew in during its final approach, cameras locked onto the object's irregular silhouette. Not spherical, but sharp, jagged, almost geometric. Its surface reflected light in uneven pulses, hinting at areas of extreme contrast. Polished surfaces next to lightless voids. Spectral scans began feeding in. Instruments searched for common volatiles, water, ice, carbon dioxide, methane, but the results made little sense. The emissions showed non-standard absorption lines, suggestive of complex organics or unknown silicates. One spectrogram even hinted at trace elements of technetium, an unstable metal that shouldn't appear in nature without active nuclear processes.